Hello and welcome back to this channel. This is already the 15th video in the series Dynamic Segmentation Inside Out. In this video I will cover how quality of services is handled with dynamic segmentation. If you want or need to know more about dynamic segmentation with Aruba networks, there's already more than 4 hours of footage that covers all the aspects of dynamic segmentation. Now, going back to today's subject, it's quality of services with dynamic segmentation. In other words, how is traffic marking accomplished so that all intermediate devices and of course the tunnel endpoint will make the right decisions on prioritizing the dynamic segmentation traffic and also traffic that has a local breakout. We can distinguish three sources that initiate the marking of traffic. Marking is either done by the end device, or marking can be done by assigning an appropriate value in the user role assignment, either locally configured on the switches or downloaded from ClearPass. Now, before I show you the proof by running some network traces, let me explain both items. First, the end device. An end device can mark specific traffic based on application or protocol, or it can just mark all traffic. So let's take a phone as example. Typically, a hardware phone marks IP voice traffic with a DSCP value of, say, 46, which is also called expedited forwarding. When this traffic arrives on a switch, the switch will recognize this value and it can then do two things. It can accept the value from the client, or it can just ignore it. Typically, if the QoS values are trusted on a port, and this is a configuration value that you can set in the switches, then the switch will accept the QoS values that are offered by the end devices. And this is actually a very common configuration in this type of environment. Now, with dynamic segmentation, when establishing a tunnel to a mobility controller, the following happens. When an end device sends a marked packet to the switch will mark the IP header, and that's the outer header with the QoS value that is set by the end device. In addition, when this packet is encapsulated in GRE, the QoS values that are initially sent by the end device are maintained. In other words, both the outer and inner QoS values are set based on the QoS values that are sent by the end device. The good thing about this is that this is done per packet. And this means that, for example, when you have a PC with a soft phone where the data traffic has no traffic marked, but the voice traffic is marked, the switch will maintain that information. And this also means that QoS is maintained across the network. And that's a good thing. In the second situation, the marking of traffic can also be defined in a user role, either locally on the switch or downloaded from ClearPass. So this is achieved by applying the marking after successful authentication. When traffic is marked through the user role, both outer and inner IP headers are marked. And if the end device already marks the packets, then this is overruled by the marking parameters that are set in the user role. And this will also ensure that the tunnel traffic will be prioritized when traveling through the network. There's also a third situation, and that is when there is no tunnel established, but traffic breaks out locally. In a situation where there is no assignment through a user role, it's just how it works in a legacy environment where you can set a trust QoS value on a port. If the trust parameter is configured, then the switch will trust the QoS values that are set by the end device. In the situation where the QoS marking is assigned through a user role, the marking is overruled by the role, and then the marking settings from the user role are applied to the traffic that comes from that end device. And that's also, again, very straightforward and simple. I think it's also important to show you the various scenarios so that you can see how this works in the real world. Now I will show you the following scenarios. So traffic marking by the end device where the traffic is tunneled. Traffic marking by the end device for different applications, where the traffic is tunneled. Traffic marking by a user role, where the traffic is tunneled again, and then the end device traffic is also marked. And traffic marking with local breakout, where a user role is applied. For the tests, I'm using a Raspberry Pi as edge device, and I will be showing you the traffic from the edge port and the uplink port of the switch. And this is the setup. I've configured the Pi to and I've connected it to port 5, and I have 3 Wiresharks connected. One Wireshark is monitoring the ingress traffic from the Raspberry Pi. The second Wireshark is monitoring the uplink. So that one is showing the tunnel packets, and the third Wireshark monitors the egress port of the mobility controller. Let's start with the first scenario, where the traffic is marked by the end device for user-based tunneling. For this I will be using the IP tables functionality in Linux on the Raspberry Pi, and initially I will be marking anything. So I'll show you that information in the trace. And then what I'll do is I'll mark the ICMP traffic using IP tables and show you how the traffic is marked on the ingress port and when the traffic is tunneled to the mobility controller. Let's start running this test. So let me first show you that the Raspberry Pi has a tunneled connection to one of the mobility controllers in the cluster. So it's got a connection to 159, and the IP address of the Pi is 10.120.1.23. Okay, let me show you that Raspberry Pi, and what I'll do here is I will start a continuous ping to the gateway. And then what I'll do is I'll move to the Wireshark that is sniffing the traffic on the ingress port. So let me start that trace, and so you can see the pings coming in here, and stop the trace. And so what you will see here is, so this is the native packet that comes from the Raspberry Pi, and you can see that the DSCP value is set to CS0. Now let's move to the uplink port and run a trace here. Okay, so that is the packet coming from the Raspberry Pi. You can see the outer IP header here. That outer IP header carries the DSCP value of CS0. So that traffic, so that DSCP value is basically copied from the inner, like from the original packet from the that comes from the Raspberry Pi, which also has DSCP value CS0. Now let me start marking the ICMP traffic on the Pi using the IP tables command. So what I will do is, so that's this command, IP tables. So what I'm doing here is I am going to mark ICMP traffic, and I'm going to set that traffic with a DSCP value of assured forwarding 21. Okay, now let's run that ping again. And then the next step is to check out the ingress traffic. And you can see that for the ping, the DSCP value is now set to AF21. So this is marked by the Raspberry Pi. And let's move to the uplink. And stop that trace. So what we see here is, let's go up. So this is the outer header. So you can see that this is the switch tunneling traffic. So 250 is tunneling traffic to the mobility controller, and you can see that for the outer header, that DSCP value is set to AF21 as well. And so GRE traffic, and the inner packet, so the original packet, also has the same DSCP marking. So this means that for marked traffic that comes from an end device, you can apply QoS because the outer header is also marked with the same value. Now, what if you want to differentiate the QoS values? So for example, you have a PC with a soft phone running. The soft phone is sending a different DSCP value than the regular data that is being sent by the client. Well, as you have seen is that the marked traffic from the client is copied into the outer header of the packet. Now let me show you by assigning a different DSCP value to TCP traffic using the IP tables command. So I'm just going to add that command. Let's move to the Raspberry Pi. And so I've got that command here. So what I'm doing is I'm setting that value, that DSCP value for TCP traffic, setting that to expedited forwarding. So that's value for 6. Okay, and now let me start a SSH session to the router. Onto that router now, and now I'm gonna move to the ingress port again. So this is the trace or the Wireshark for the ingress port, and let me start that. I need to obviously now filter on SSH, and let's do that. And you can see some SSH traffic coming in. And what you can see here, the DSCP services field is set to expedited forwarding. And now let's move to the uplink and see if we get some traffic here. Of course, I need to change the filter. Okay, and so this is the packet coming from the Raspberry Pi. You can see that the outer DSCP value is set to EF, and so that's the same for the original packet, which is also set to EF. So this shows you that when you mark traffic from an end device perspective, you can perform QoS that is based on the markings that are done by that end device. And those markings can be different based on the applications that you're using. And that's pretty cool. Now let me show you now what happens when you assign a DSCP marking through role assignment in ClearPass. And in addition, I would still have the client perform marking. So in this scenario, basically the same will happen with regards to marking using user roles, which is that the marking is applied to the outer and inner IP header. So as a reminder, for the ICMP traffic, I am marking the original traffic with AF21, and for the TCP, so for the SSH traffic, I am marking with expedited forwarding on the Pi. So this means that when I apply the DSCP markings through a user role, I should not see these markings on the tunnel to traffic anymore because I'm using different DSCP values in the user role. So I should still see the AF21 and EF markings on the ingress, but not on the tunnel to traffic. Okay, so let's move to ClearPass and let's see what the access tracker is saying for the Raspberry Pi. So the enforcement profile that I'm using is the UBT DUR Pi. So what I'm going to do is I'm going to move to that profile. That's the DUR Pi, and you can see in the user role configuration that I have some classes here for SSH and ICMP. So what I'm going to do is I'm going to make some changes to those classes. Okay, so that's the policy, and in that policy you can see that I am permitting ICMP and I'm permitting SSH. So what I'm going to do is I'm going to edit that rule, and what you can see here is I can have a DSCP value set in this rule. So what I'm going to do is, so in the original packet I have assigned AF21 to ICMP traffic. So what I'm going to do is, let's say I'm going to assign AF31 DSCP value. AF31 is the same value as the DSCP value 26. So that means that for ICMP traffic, I should now see DSCP value 26 instead of DSCP value 18, which is AF21. Okay, and let me do the same for SSH traffic. So I'm going to change that value so that the initial value that comes from the Raspberry Pi is 46, which is expedited forwarding, and I'm going to change that to value 38, which is the same as a short forwarding 43. Right, so ICMP AF31, so 26, SSH traffic AF43. Save the rule, save the policy, and then save the profile. And the next thing I have to do is I have to bounce the port so that a re-authentication takes place and that the new user role is applied to to that device. So what I'm going to do is change status and do a bounce switch port. Okay, and I should see that accept coming in. So that's this one. And so no, it's not this one yet. So I need to wait for a second, I guess. Let's see what's happening here. Yeah, okay, so this should be the one. And you can see now that those values are pushed to that client. So this is the user role, and these DSCP values are assigned. So for ICMP, DSCP value 26, and for SSH, DSCP value 38. Now let's move to the Raspberry Pi and perform the ping. So let's first check out the ping. See what is coming into the switch. Again, so change that to ICMP. Should get some ICMP traffic in, so that's cool. Okay, so for the ingress, you can see that I still have AF21 coming in. And now let's move to the uplink. Change that back to ICMP. Okay. So on the uplink, I should see a different value, and as you can see here, that value is AF31 instead of AF21, and that also applies to the inner header. So what happened here is that the switch remarked the original packet that came from the Raspberry Pi and remarked that packet to AF31. Okay, and let's test the SSH. So that should change as well. First, the ingress port. Okay, let's do this a couple of times. and see what's happening. So you can see on the ingress, I'm still using the expedited forwarding DSCP value. And let's check out the uplink. And of course, I need to change that filter again. SSH. And you can see here the outer header has a different DSCP value, AF43, and the inner header should have AF43 as well. And so that means that so as soon as you start to use user roles, the user role values, the user role DSCP values will have precedence over the DSCP values that are set by the end device. Now let me show you another cool thing. In the previous examples, I've worked with DSCP values, but with dynamic segmentation tunnels, you can also assign an 802.1 P value. Now, before I do that, let me just show you what happens with the P values in general, because there is something weird going on, and let me show you that. So what I'm going to do first is I'm going to issue a ping from the Raspberry Pi to the gateway, and now let me just run a trace on the uplink. So you should see that ICMP traffic here. And if I go into the virtual LAN field here, so this is the GRE header, and you can see that the GRE header contains an 802.1q header. Now what you can see in the 802.1q header is that the priority, the P field, is set to 3, and that is strange because I haven't configured any P values. Now the reason why this happens is the following. Let me explain what happens. Is that so the DSCP value is AF31. Let me show you the switch, and let me do a show. Let's do this. So QoS DSCP map, and let's check out the 31 AF31. So that AF31 is mapped to p-value 3. So what that means is that when the switch assigns the AF31 value, DSCP value, to the packet, it will also assign the p-value of 3 to the p field in the 802.1q header, and that is what you see here. And I can prove that by changing the profile. So let me just move to the profile, get the policy running, policy config here, and let me just remove that DSCP value and set it to the default value. So what should happen is I should not see that p-value. Well, I should see a p-value, but that p-value should be 0. Okay, let me just bounce so terminate the session again and see if that ping comes back. Yeah, ping comes back again, and I'm gonna run that trace again of the uplink. Okay, and then let's see what is in that queue header. Priority is set to 0. So that proves that as soon as you set the DSCP value, so now it's AF21, but as soon as you set the DSCP value, then that p-value, that 802.1 p-value, is assigned by using the QoS mapping. Now the cool thing I can do now is in the profile, so I can overrule that QoS mapping by configuring another p-value in the policy. So let me do that for ICMP, so I'm gonna change that to 20. Oh, well, change it back to 26 again, and I'm going to set the priority, the p-value, to 4. I'm gonna do the same with DSCP, but for DSCP I'm gonna set the p-value to 6. Okay, bounce the port again. Okay, and so let's see if my ping is still running. Ping is still running, and let's see what's happening in the trace. So I should see a p-value of 4 now for ICMP. Let's check out the trace, and yes, you can see the priority field is, the p field is set to 4, and my DSCP value is derived from the profile again, AF31 instead of AF21. And so also let me change that to SSH, and let me open an SSH session to let's see, that one. Okay, run a trace again, see what's happening with the SSH traffic. Okay, see some SSH traffic here. So I should have a priority value of 6 in here, and you can see that is the case. And the DSCP value is set to AF43. So that's pretty cool. Now what I would like to see happening is that the egress traffic coming out of the mobility controller, so that's the untunneled traffic, so that's the original packet, I want to see that P marking and DSCP marking on those packets as well. Now for that I have a different Wireshark running. So this Wireshark is running on the egress port. Let me just run that trace here, and let's move back to the SSH session and just hit enter a couple of times. So I'm seeing some traffic here. Let me show you the traffic that is coming from the Raspberry Pi going into the router. So you can see that this is like a standard frame, so it's not GRE. It is carrying a 802.1q tag, and my virtual LAN header is here, and you can see that P field is carrying the value of 6. If I dig in a little deeper into the IP header, you can see that the DSCP value is set to AF43. So going out of the controller, the P values and the DSCP values of the packets are preserved. So they're not stripped or anything. They're just egressed on that port. So that's also pretty cool. Okay, now let's move to the last scenario, and that is marking traffic for devices with a local breakout. So that is no tunnel. For this I will be using an IP phone that is connected to port 3 of the switch. First I will show you the traffic on the uplink without traffic marking, and then I will apply traffic marking in the user role for the phone and check out the trace again. I hope that you're still with me. If not, just go with the flow and I will go through the scenario step by step. First I will show you the phone profile in ClearPass. Let me show you the access tracker here, and so the enforcement profile that I'm pushing for the phone is DUR phone. And that means that I have to check out the phone profile here. And what you can see in this profile is that I am pushing a class, all traffic, action permit, and I am pushing VLAN 140. So it's VLAN 140 on the axis, and I'm trunking that VLAN, so I'm tagging that VLAN on the uplink port. Now let's move to the Wireshark. So here's the trace. I've been running that trace for a while. As you can see that there are DNS requests sent from the phone to the DNS server. And let's check out one of the packets. You can see that there's a 802.1q header in here. Priority set to 0. And in the DSCP field, you can also see that the DSCP is set to CS0. So that's all default values. Now let me move back to ClearPass and change some values here. So the first thing I need to do is that I need to create a class. Oh, sorry, I'm doing something wrong here. I need to edit this one. So let me just expand that a little bit. So I need to create a class. That class would be IPv4 DNS, and I am matching UDP traffic equals 53. Okay, need to add an exit command there. And what I also have to do is I need to add this this class to the policy. So what I will be doing is the following. I will be adding this line here. So adding a rule, adding a class to the policy, saying so this is the DNS class. I'm permitting the DNS traffic, and I am marking that traffic with DSCP value 46 and assigning a P value of 6. Okay, so I'm going to save that one off and save the profile. And then next what I'm going to do is the bounce the port so that a re-authentication takes place. So I'm doing a port bounce and close, and I should see an accept coming back in a few seconds. Okay, so here's the port bounce. Let me check the response. Yes, so you can actually see that the rule is applied. So I've got this class created, and that class is applied to the policy. So that means that if I go back to the trace, I'll just run the trace again. When I get a DNS request coming in, and that's here. Let me just stop the trace there. There should be a priority field should be set to 6, the P field, and that's what's happening. And you can also see the DSCP field on the inner header set to expedited forwarding. So that's cool. As in the UK they would say, Bob's your uncle. I don't have a clue what the source of this proverb is, but so this means that, you know, we can all get this stuff to work in a proper way and really mark traffic in a very structured and programmatic way, which is pretty cool. And this concludes yet another video in the series Dynamic Segmentation Inside Out. If you have any ideas or suggestions, please let us know, and I would like to thank you for taking the time to watch this video and this video series. Make sure that you subscribe to this channel so that you're up to date with all the great stuff that is coming to you from Aruba Networks. So thanks and bye-bye.